Well, welcome everyone, and welcome back to the first Project Blue live chat of the fall. We're excited to be back, and our first guest this year is Dr. Greg Stone. Welcome. If this is your first time tuning in to one of our events, welcome, and we're glad you can join us. We'll be doing a Q&A conversation following his presentation, so please feel free to ask any questions you might have in the Q&A function or the chat below. Now, before I turn the floor over to Dr. Stone, one big announcement. AltaSea has recently announced their second annual Blue Hour. It's their annual fundraiser that celebrates AltaSea's partnerships and future. Blue Hour, Ocean of Inclusion, will honor 3 ocean innovators: Schmidt Ocean Institute, Philippe Cousteau Jr. and Earth Echo International, and Robert Downey Jr.'s Footprint Coalition. So join us on October 9th at Angels Gate Park in San Pedro, which is right next to the Korean Bell of Friendship. Tickets are going fast, so be sure to get yours today at altasea-project-blue.org. And as a thank you for joining us today, use the code AQUA and you'll get 20% off your tickets. And I'll put the link to the tickets in the chat once we get started. Now to our guest. Dr. Greg Stone is the Chief Ocean Scientist for the Metals Company. He's an ocean scientist and explorer with over 10,000 dives throughout Earth's ocean, down to 18,000 feet using submarines, scuba, underwater habitats, and robotics. He's widely known as a global thought leader who finds ways for humanity and the ocean to coexist and support each other in the modern world. Dr. Stone, welcome. Thank you again for joining us. And again, if you have any questions, Q&A and chat, we'll answer them at the last part of this chat. The floor is yours.
Oh, thank you, Jacob. And hello, everyone. And I'm so pleased to be back here with AltaSea. One of my very, very favorite organizations. When I first encountered it, I met Jenny Crusoe, the executive director, and others, and I feel it's one of society's more important NGOs at this point in history as we look to the sea to both have an economy based on the ocean, but also protect the ocean and really engage with the ocean. So today this is the second time I've had the privilege of being on this program. Last time I gave a general ocean talk. Today I'm going to focus in a little bit more on how we're going to transition to the renewable energy future that we're all so eager to get to, so we stop burning fossil fuels, and what role the ocean may play in that. So the presentation is going to have a little bit of a wind up in terms of going over some things that we talked about last time, but then it will focus in on some work I'm doing with the Metals Company with polymetallic nodules. But let's advance the program here. Let me see if I can get it to advance. There we go. Okay, you all may remember that the ocean is driven fundamentally by the ice at our poles. Having ice at our poles is a very important part of the Earth atmosphere, ocean, terrestrial system, because it makes the ocean flow through a system called the Thermo Haline circulation pattern. And you can see it here in this graphic. Basically, water gets cold at the poles, it sinks, and as it sinks, it draws water with it, and then it travels along in deep ocean, and it's like a big conveyor belt. Once it gets going, it just keeps going, but it expresses itself in various ways around the planet that you will notice. One is the Gulf Stream. You can see it there in this picture right now. It's all those arrows going up to the north. And that's the biggest transfer of heat from the South Atlantic to the North Atlantic. It's also what makes Europe so mild, the climate there so mild. And then around Antarctica, you can see there's something called the Antarctic Circumpolar current, which goes right around the globe. And that's kind of the organizing principle, if you will, of all the currents, is that one. And the water at Antarctica sinks, as does it at the North Pole. And this sinking to the bottom is what drives and gets this conveyor belt going. Back in the Miocene, 25 million years ago, we didn't have ice at our poles, and the oceans were stagnant. It's this dynamic nature of the oceans and from these currents that makes them so productive. Now, just to show you one of the ways, there are many, but one of the ways to study the ocean, and the Earth is 70% water. I mean, really get your head around that. The 70% of the planet that we're on is water, 30% is land. So it's not surprising that we have only recently begun to really understand the ocean. Most of our existence as humans, hominids, has been on land, and that's because that's where we focused. Now, when we go to the ocean, we need special equipment. This is a research submarine, a very specialized type. It's the type that goes down very, very deep. This one can dive to about 5 miles or so down, straight down. And I've used this one myself, so I put it up there. And when I first dove this submarine, this particular one, it was in the Sea of Japan. And when we got to the bottom, I was really surprised to find what I found, which was a lot of trash. And this was an area that had not seen the light of day. Excuse me, I'm going to shut a window here so it's not so loud. This is an area that had not seen the light of day for literally billions of years. Yet here I was, the first person to go there. I know no one had ever been there. And already you saw the footprint of humanity. And this picture was taken back in the early 90s. And it really, at that time, startled me and fundamentally changed my career path from pure research to a more applied work. And I went to work with the New England Aquarium first, started their ocean research and conservation program. And then I went to Conservation International, where I was the chief ocean scientist. And now I'm working with the metals company. In between there, I also worked with the World Economic Forum and the UN. And I feel in some ways the work that I'm doing today is perhaps the most important work of my life in terms of making our existence on this planet work. And we'll get into that a little bit later. But the oceans, we came from the sea. This is supposed to be a humorous look at what's really a tragedy, in that we came out of the sea, all life began in the sea, and then we get up on land and we evolve into these creatures with this brain that some say is the most complicated thing in the universe, because it's got, I believe, about 200 billion neural connections. And it's the brain, it's our brain that really has set us apart from all other animals. 30% of all the calories you eat every day goes to your brain, to give you a sense of how important it is. And it's what enabled us to leave Africa and ultimately populate the whole planet. But we only finished that population in this last 100 years or so. That prior to that, we were still working our way towards complete domination of the planet. Now we've done it. We are the only species that exists everywhere. We are the only species that has the ability to change the conditions on Earth like the weather. We are the only species that has the power to act like a force of nature through our activities, and ranging from the way we dispose of garbage and trash to polluting our atmosphere with carbon dioxide, methane, and other gases that have produced the greenhouse effect. So this really is a different kind of a planet today than it was even 200 years ago. And we are now part of this planetary, global, ocean, terrestrial, atmospheric system where we've become part of the ecology of the whole planet. And we have to look at it that way if we're going to get this right and stop destroying the planet. This is some video of a dive that I took just recently,
Turn near and some of these
off
rocks.
the coast of
Very cool.
Hawaii,
Should be hanging.
and that I'll leave that sound on. The way it works in these submarines is there's always a recorder going on inside the sub, recording all of the conversations that are happening, so that you can go back and pick up information that was in conversation. Now, we came around and saw this gumbo octopus, which is a fairly common creature down there, and a bit whimsical and kind of fun to look at. This is, I was diving on a seamount about 100 miles south of Hawaii, and we encountered this animal. But it gives you a sense of what the underwater is like. And this is down at around 2,000 to 3,000 meters on top of a mountain. Most people are surprised to learn that there are more mountains in the ocean than there are on land. It's really quite astounding that ocean that you see out there that looks so placid and flat is really covering up a very dynamic set of mountain ranges and trenches and topography that plays a fundamental role in providing habitat. In also those currents I talked about earlier, they affect those currents. One way they affect those currents, and another way those currents are important, is that when they come back to the surface, that water that sinks in Antarctica that I mentioned at the beginning will go to the bottom of the ocean, and it will go very slowly, just sort of creeps along at a snail's pace, and it can stay down there for hundreds of years, some say maybe 1,000 years at times, until it gets back to the surface. And one place where it does come back to the surface is off the west coast of South America. And that's what makes the Galapagos Islands so interesting. And I was just there 2 weeks ago with National Geographic, looking at the biology of the Galapagos. But the whole western side of South America, around the equator, is highly productive. It's the most productive area on the planet. It's because of this cold bottom water. We call it Antarctic bottom water. It's finally made its way back to the surface after this long journey along the seafloor. And it brings with it nutrients, oxygen, and other things that are in it. So that's why you get so much productivity very often along the west coast of any continent, but especially around South America. And what you see here is a ctenophore sea jelly. You're not supposed to say jellyfish anymore, I'm told, because they're not fish. Although everybody uses the word jellyfish, I don't mind if you use it, but you'll get scolded by some scientists if you say jellyfish, because they're not fish. They're an invertebrate animal with no bones, nowhere near a fish in the taxonomy. But this doesn't have a common name. I call it Darth Vader sea jelly, ctenophore. This is the kind of animal that you'll find when you go down a few thousand feet in the ocean. I'd also like to get you to rethink what the ocean is, because we tend to compartmentalize things so often. And the ocean really is, it's a complex system of how water is managed on our planet. It starts off in the ocean, and then it evaporates. About every 33,000 years, the equivalent volume of the entire ocean evaporates up into clouds. Every 33,000 years, the equivalent volume of the entire ocean evaporates up into clouds. And as it evaporates, it purifies, because it leaves all the elements and things that have been in it in solution behind. It's kind of a miracle, actually, the way the water is able to separate from everything else, turn into a vapor, and get up and make a cloud. And then the clouds drift over the land, and they form the weather that we're all so used to. And the weather often associated with rain. And then the rain comes down on the land, fills the rivers, and then gets back to the ocean. So in reality, the ocean is this whole system. It's the salty part that we all know about, but it's also the water rising in vapor up into the clouds. It's the clouds and the weather. and it's the water that hits the land and goes down through the land. And by the way, every time it sweeps down through the land, it gets saltier. The ocean is continually getting saltier over time. Our blood is about half the salinity of seawater, and it represents the period of time when animals came out of the ocean. So when our ancestors, and they were not humans, they weren't even primates, came out of the ocean, they had the same salinity as the ocean because that's what they lived in, and we carry a memory of that time in our blood today. But the reason it gets saltier is, imagine water sloshing around in a bowl. It's always going to be picking away at the sides of the bowl, and the elements and nutrients fall into it. So if there's one thing you walk away with today, it's a more expanded view of the ocean, because what you do on land affects the ocean. What you do in the ocean affects what happens on land. They're all connected. Now I'd like to take you through a framework that I developed with a co-author of my last book, which was called The Soul of the Sea in the Age of the Algorithm. And we decided to take a look at the world over the last 50 years or so. And we realized that you could break it up into decades of, we called them doctrines, or a framework of how we look at the ocean, how we interacted with the ocean, what happened. And I'd just like to run you through these to take you to the present. The 1950s was an interesting decade because it was after World War II. And one of the most important things from our point of view was the invention of the two-stage regulator by Jacques Cousteau. And that suddenly, for the previous hundreds of thousands of years, our species was not able to get into the water very far. We could maybe swim down 50, 60 feet, but we really couldn't have a good look around and understand it. But the scuba, the development of this affordable method of diving, the two-stage regulator by Jacques Cousteau, really opened things up, and it showed the world what was there. The reason I call the 1950s the militarization of the oceans is because after World War II, normally countries, after they finish a war, they kind of demilitarize. Certainly the case in the United States. If you look back, the Revolutionary War, the Civil War, and World War I, after each of those conflicts, we tended to disassemble our military and get back to civilian operations. But because of the Cold War, that didn't happen this time. And instead, we took the Cold War to the ocean, and in the form of nuclear submarines that would drive around with nuclear warheads on them. And the ocean became the battlefield of the Cold War. There was a lot of cat and mouse games being played. I got one time when I was out at sea doing research, I saw about 6 American military vessels. This was off the coast of Bermuda, and there was one Russian military vessel, and they were all harassing each other. It was part of what they do in Cold War times. One ship would launch a helicopter to fly over the Russian ship, and the Russian ship would launch a helicopter and fly over the American ship, and they were just sort of poking fun at each other. Hopefully, you always hope nothing's going to come of it. But the more ships and submarines were built during the 1950s than during all of World War II. Give you an idea of how militarized the ocean became during the 1950s. But as I said, the scuba tank also opened the oceans up. And in this graph, we call it the civil awakening. And it was the time when we started to, anybody could go into the ocean and see what was there. And it was a time of discovery, a time of wonder. It was the time when I was growing up watching these TV specials on the television that Jacques Cousteau and others were doing, and it brought the ocean into my life. Very important part. And it was the beginning of the emergence of organizations like Greenpeace and the World Wildlife Fund. Rachel Carlson famously published her book, Silent Spring, in the 1960s. And that led to awareness of a book she had published about 10 years earlier called The Sea Around Us, which has now become a classic. So the 60s was a time when civil society, kind of woke up to the ocean and that it was important. And then if you go into the 1970s, we look at a different kind of engagement. Now we're getting civic engagement through laws and through the development of departments and ministries in governments. In the United States, NOAA, the National Oceanic and Atmospheric Administration, was founded in, I believe it was 1972. So it was kind of a response to what we had learned in the 60s and 50s, that there was something important out there. And a couple things started to emerge. The London Convention on Dumping in the Sea was passed in 1972. The United Nations started to get more involved. And by the way, the bar charts along the bottom are the number of treaties, international treaties that were signed by year, and that involved the ocean. And you can see the increase over time as we became more aware. We came up with more treaties and laws. The 1980s, we playfully call here the Viva la Revolution. And that's when we really saw deeper engagement with the ocean, and some fairly major actions were taken. One in particular was the cessation of whaling, finally. The other one was the UN Law of the Sea, or we call it shortly UNCLOS, in 1982. And this is like the constitution of the oceans. Because the oceans, remember, there's 70% of the planet, a lot of the planet, we didn't have any framework to interact with the ocean or with each other vis-a-vis the ocean until UNCLOS was negotiated and passed. And it's considered to be one of the finest pieces of international legislation ever. It took on lessons learned over the last couple hundred years of industrialization and tried to look as best it could into the future, and built a framework for what may come, including the possible extraction of minerals from the sea. That was a large component of the law of the sea, was contemplating if we went out into the ocean on the high seas are the place that no one country owns. We all own it. That area belongs to everybody. Each country gets to possess 200 miles of ocean along its coastline, and including what's on the seabed. But beyond that 200 miles is high seas, or common property of everybody that lives on the earth. And that was all worked out in the 1980s. And then in the 1990s, we see the emergence of the private sector engaging with the ocean. They kind of realized, oh, wow, this is pretty important. We better do something about this. And we have things like the Marine Stewardship Council came into being, which is a council that was started by seafood retailers and catchers to certify seafood that was caught in an appropriate way. We have more conventions. We made progress in the Arctic Council was formed. The first Rio Earth Summit famously was held in the 1990s. And that's when the whole world got together and said, hey, the environment's important and we need to work together on this. We now have these, we now have these meetings like we had in Rio every 20 years now. We just had one, actually. So we renew this global sit down and commitment to the ocean and what we should do about it. In the 2000s, it was a very optimistic time, I think, in many ways. We had learned so much over the last 30 years, 30, 40 years. We learned how the ocean was put together. And that was started by the military's interest in understanding the ocean so that submarines could hide and move through it. And the birth of modern oceanography occurred during that period. We also learned by the end of the 1990s that the oceans were in big trouble. The National Academy of Sciences published a book called The Conservation of Marine Biodiversity. And that book identified the 5 major threats to the ocean that humanity poses. And those threats pretty much have stayed the same. You might argue that you could add one, but they are biodiversity loss, it's overfishing, climate change, pollution, coastal development. And that set us up for the 2000s, where we knew the problems, we understood the ocean, how it operated a lot better, and we needed solutions to the problems that we found. And the solutions were pretty much developed in the first decade of this century. Things like the creation of marine protected areas. That was not really a thing that we had up until then. Fishery management went to a new level where statistical scientists would predict how many fish you could take without collapsing the stock. We had the tools came forward, and it was a question of applying those tools, not knowing what they are. So we went from pretty much ignorance about the ocean to a point of understanding how it works, understanding the major problems, and also having a growing toolkit of tools that we could apply to fix those problems by 2010. Now we're in what some people call the 4th industrial revolution. And as you look back over time, there were key moments in civilization where we discovered something new or figured out how to make something, and it turned into an era. It was a step change in our civilization. I'll give you a couple of examples. We started off working with stone tools for a long time, millions of years. Hominids just means a primate that walks on 2 feet, and we're a hominid, and we've been making stone tools for literally millions of years. But then somebody figured out that there was bronze, that you could make bronze, a metal, out of elements that they found in the earth. And that suddenly you had this solid substance that made a good weapon. It made a good cooking pot. It made a good piece of armor. It was very, very handy. Bronze right into the Iron Age. It's another metal similar to bronze, but much harder, much better swords, much more durable. And then we went into the age of oil, is probably the next big step change, and that's when we were able to burn oil and harness the energy that was captured and locked in that oil, the fossil fuels. And the fossil fuels, by the way, you should consider where they came from. They are deposits of hydrocarbons that were deposited, a lot of them during the Jurassic period, when we had a lot of plant life on the planet. We had dinosaurs, lots of biomass. And when that biomass died, and under certain conditions, it would lay down layers in the ocean, and those layers would then get sealed off. And over time, it would transform itself from sort of organic waste into a fossil fuel that you could burn. And that's how the Industrial Revolution of late, the mechanical Industrial Revolution, was fueled by machines that burned this oil and this gas and this coal and turned that heat into mechanical motion, and it revolutionized manufacturing and transportation and all kinds of things. Now we're in the age of the fourth industrial revolution, and I would argue that this could be called the age of metals, because we know that we can't and don't want to keep burning fossil fuels. That was a very unfortunate mistake that we did, because the unintended consequence of burning all those fossil fuels was that we changed the climate of the planet at a very fast rate. Change has always happened on planet Earth. Change will always happen on planet Earth, but it's the rate of change that's key here. Prior to this, it took a lot more time for things to change. For example, to get as hot as it did during the Jurassic, that the heat and the climate during the Jurassic on the Earth was like, think Bahamas everywhere. It was that warm, and it was great conditions for growing plants and capturing a lot of carbon in those plants and the dinosaurs and all that. And then that organic material got locked away, transformed itself into fossil fuels, and now we're burning it, right? So as you burn gas today, you're actually burning energy that was locked away by maybe a dinosaur or some other animal that lived many hundreds of millions of years ago. So we're burning fossil fuels that were created during a hot period of our planet, and the effect that that's having is to heat the planet up again, but at a much faster rate. The Earth is warming now some 4,000 to 5,000 times faster than it did when the first Jurassic period arrived. So we've got to use the same brain, the same smarts that got us into this problem to get us out of this problem. And that's a lot about what the fourth industrial revolution is about. And I wrote a book about this, and in it, my co-author and I, Nishan Dignarian, we posited that it's high-tech or companies may be part of the solution, because we needed innovation, we needed new thinking, we needed fast action. And in fact, it seemed to be that is exactly what is happening since the book was written. So here's another way of looking at this. This is a graph of time starting 50,000 years ago, and it goes into the future. And if you notice on the left, you've got primitive technologies and primitive ways of living, and you've got a lot of ocean life, pretty healthy. And then in the middle, you've got the industrialization, where you've got fishing nets taking too many fish. You've got not much care for the coastal environment, and that's the problem. Now, as we go into the future, it's my hope that we will have an optimistic future, that we will take on all the lessons learned, and through the fourth industrial revolution, we will engineer our way to a sustainable planet. Because right now we're not operating in a sustainable way. Every year, there's one day, it's called Earth Overshoot Day. And it's the day that we use all the resources allocated for that year if we want it to be sustainable. Anything we use after Earth Overshoot Day in any particular year is coming out of our future, and means that we're heading down a dead end. We're on a train that's going to go off a cliff unless we change our behavior. This year, I believe Earth Overshoot Day was in June sometime. The year before that, it was in August. So it's moving in the wrong direction. Now, how are we doing? Well, the news, some of the news is good, some of the news is not so good. This is a map that shows the location of all the marine protected areas in the world. those dark blue areas are protected. And there's not enough of them, really. We need more. We can't protect the whole ocean because we need it for certain things. A lot of people feed themselves every day out of the ocean. In countries that are impoverished but live along a coastline, they won't have a refrigerator, but they do have the ocean, and they'll go out each day and get some fresh food out of the ocean, and they rely on it, and they are really part of the ocean ecosystem. I was involved in working on a protected area. It's this box right here. It's the size of the state of California, and it was the first one of all these big ones you see. This was created by the country of Kiribati, and I was working with them on this starting 20 years ago, and they boldly made the world's first large-scale marine protected area, and other countries followed, as you can see looking around the map. But it's been done in a bit of a haphazard way. There's no really rhyme or reason to it. We should be planning very carefully protected areas so that we protect those areas that the animals absolutely have to have undisturbed, so that we can have other areas where we can come in and have our needs met as a burgeoning population. I'm going to show you a very short film here. This is some other research I'm involved with through the Metals Company, and also through a nonprofit organization I co-founded a couple of years ago called Pole to Pole Conservation. And I'll just run this. It was a documentary by The Economist magazine, and it's only a few minutes long. Can you hear that, Jacob?
Any attempt to conserve areas of the ocean properly brings a host of challenges, not least when it comes to protecting the ocean from its greatest threat, climate change. This is forcing a major rethink about how marine protected areas should be designed and selected in the future.
Well, we're at the end of the world, and now we're going off the grid. The plane is jam-packed. I hope it gets off the ground.
Dr. Greg Stone is one of the leading scientists in this field, and he's taking a team to one of the most remote corners of the globe as part of his latest research.
It really is one of the last places that it's hard to get to.
Beautiful. Look at that. Hello, Canton.
This is Canton Lagoon. We are in the heart of the Pacific Ocean. To get here, we had to fly to the furthest commercial destination that I'm aware of in the Pacific. And then from there, we chartered a plane to take us another 400 or 500 miles to here, Canton Island. Our closest human neighbors, well, they're up in the space station.
Canton Island is part of the nation of Kiribati, right in the middle of the Pacific, 2,000 miles from Hawaii. They hope to find out how resilient these reefs might be to warming waters. The destruction of coral reefs as a result of climate change is disastrous for the ocean's ecosystem. So this is high-stakes research.
Let's get suited up, guys. Yeah, this looks pretty good. I guess we'll probably drop in right at the bow. Okay. It looks to me like the coral's in pretty good shape now, so we're in a good moment to get these instruments in the water.
The plan is to install around 10 thermometers on the lagoon floor.
What we've got here is a long-term underwater temperature recorder that will record the sea temperature every 30 seconds for the next year or two. And we're going to fasten it to the reef, and these are buoys to help us find it a year or two from now. And this will enable us to understand the temperature changes. You get into the water and you feel the energy, the photosynthesis, the production of these amazing corals. And you look at them, and they're so vibrant. It's clear enough, though, so you can see everything. It's just like, wow, the ocean's alive. It's really a magical place.
Coral bleaching is one of the major kinds of damage inflicted by climate change. But previous research has suggested that the coral here has a rare ability to survive.
We've witnessed two major bleaching events that have come through here. And when it first happened about 17 years ago, we were all so depressed because we thought that was the end of this spectacular system. Just very depressing, dead, brown, black, broken coral. And we almost needed Prozac to try to cheer ourselves up. It was so bad. But then it bounced back with incredible vigor. It was almost like finding someone who was almost dead, get up and walk the next week. Never had we seen a reef system respond like that.
With another temperature hike potentially brewing, Greg is hoping this latest research will provide more evidence to suggest that this coral is equipped to resist climate change.
So it turns out that coral has been subjected to periodic oscillations from El Nino for thousands of years naturally. The El Nino oscillation is a occurrence that happens every 4, 5, 6 years, where the surface water gets very warm, and it sometimes makes its way all the way to South America. And because of that heating, the constant heating, it looks like Darwinian natural selection has bred coral that can withstand heating much better than areas where the temperature regimes are stable. For example, the Great Barrier Reef is in a part of the ocean that doesn't change much. And as a result, we see the Great Barrier Reef is really struggling right now because of the warming water, whereas the coral here is dealing with it. And it could be that in the future, these corals could be transplanted, perhaps. There's a lot of work to be done before that happens to make sure it's safe and that it would work. But one of the projects that I'm working on is studying this coral and seeing if it can be grown in a nursery and then transplanted someplace else. And this expedition was sponsored by the Metals Company and also by Pole to Pole Conservation and a anonymous donor. And the results were very useful in understanding the heat that came in during an El Nino about 2 years ago. And why are we so worried about all this? Well, it's because the oceans are what makes the Earth a nice place to live. If we didn't have them, we wouldn't want to live here. They produce all these benefits that you can read on the screen here. I won't read them to you. You can read them yourself, but you can see that they feed us, they regulate our climate, they provide jobs. It's a very important part of what makes Earth a nice place for us humans to live. The challenge ahead of us is that it's estimated that our population is going to keep growing at 80 million people a year to the point where we might have as many as 9 billion people on the planet with all the stresses on resources that those new people will bring. And how do we maintain a livable planet and take care of people that join it? We're going to need twice as much food, twice as much water, twice as much energy that we currently have, and we don't have it. And the last time I checked, there wasn't another planet nearby that had this kind of abundance. So we really have to focus on Earth and get it right. We've got to use, as I said, our brain and the fourth industrial revolution to solve some of these problems. Another great issue of our time is sea level rise. The heating of the ocean is causing two things. It's causing thermal expansion. The ocean is swelling because it's getting heated, so it swells and the volume gets greater. And then it's melting ice. It's on the land, these glaciers. And that as glacier melt enters the ocean, it rises to sea level. This is a country, the country of Kiribati, in the middle of the Pacific Ocean, where I've been conducting research for many years, and they're already having a hard time with it. Their land doesn't come out of the water very high at all, and when there's a storm or big waves, they wash over the island, take the roads out, and it's predicted that this whole country might be unlivable within about 100 years. And think about that for a bit. Here's fellow, what are we, Earthlings, and some of us are going to have a much harder time with climate change than others. And the irony is that the people that are going to suffer the most from climate change are the people that had the least to do with causing it. They didn't burn much fossil fuel. The fossil fuel and the gases associated with it were produced by the global north or the developed countries like Europe, America, and increasingly China. So we have to think about our responsibilities to these fellow Earthlings and what we've done to the planet that's harming them. It would be like if you lived in a neighborhood and you had a party, a wild party in your yard, and by accident you lit your neighbor's house on fire and burned it down by accident. You didn't mean to do it, but it happened. And now they're out in the street with all their belongings and they got no place to live. And it was your fault, but we're not taking responsibility for it. Instead, we're looking at these situations and going, "Oh, that's so sad. What are we going to do? What are they going to do?" And people tell me that when I give talks like this, and I often correct them immediately and say that's the wrong question. The question is, what are you going to do? Because you and I'm included in that group created the problem. So something to keep in mind. There's a vault up in Svalbard, and it's an old coal mine where the temperature is and humidity is very, very constant. And somebody had the bright idea to turn it into a seed bank. And it's got over 1 million varieties of seeds in it. And it's there because it contemplates what would happen if the climate changed so badly or some other disaster happened that we lost a lot of the plants that have evolved on the earth to support us. This vault is insurance, an insurance policy. Some people call it the doomsday vault. And the idea is that if the earth did get into a really bad way, somehow somebody would make it up here to this vault, break into it and start anew. Oh, I've got to get going. I just did my time. Okay, so now I'm going to spend the last few minutes here talking to you about the special case of polymetallic nodules. There are 3 kinds of ways of getting metal out of the ocean or deep sea mining. One is cobalt crusts, which is tearing the tops of seamounts off because there's a lot of cobalt there and other valuable metals. Very destructive method, which I don't support. The other one is to go to extinct hydrothermal vent fields and knock down the chimneys that form when hot water pours out of these areas. And those chimneys are also full of valuable metals. I don't support that as well. It's also very destructive and not really necessary. However, these polymetallic nodules are a special case. They form on the bottom of the ocean over long periods of time, and they take on the characteristics of the seawater around them. Remember, water is the universal solvent. Everything dissolves in water, including metal. And they accrete, the metal accretes to something. It's usually in the middle of one of these nodules. There'll be a shark tooth, a piece of sand, something, a piece of shell. that starts it, and then the metal slowly accretes atom by atom over millions of years until you get a rock that is got the metals that we need for batteries and for other metal needs in our society. And the best place for that is an area called the Clarion Clipperton fracture zone, and it's about 1,000 miles west of Mexico. And this whole area is about 1% of the seafloor. It's not a very big area when you compare it to the whole ocean. And all these marks you see here are lease sites that different countries have claimed through a regulatory regime run by the United Nations. It's a very organized group called the International Seabed Authority, and they are based out of Jamaica. And they're the regulator of this potential industry to bring metals to the surface and meet the demand that's coming. It's the demand for some of these metals to have a renewable energy future is anywhere between 500 to 1,000 times more metal than we currently have. And we don't have enough in circulation currently to recycle our way through this. We need an influx of virgin metal. And then once we have the virgin metal, we need a robust recycling system for that metal so that we can get to a point where we don't need to collect anymore. Now, this is what I'm going to show you now is this is a video shot of a camera that the metals company, we put it on one of our buoys. We're in the middle of conducting an environmental impact assessment to see what the effects would be of collecting these nodules. And the camera took 3 frames a day on the seafloor. So I'm running it now, so it's essentially a time lapse. You're watching 3 months of activity, and it's hard to tell that there's anything going on because there's so little life down there that you can see. You do see little flickers here and there. That's a fish swimming by or a starfish moving along the bottom, but it's a fairly depauperate area compared to coral reef or more shallow grounds. And these round objects are the polymetallic nodules that I mentioned. They're about the size of a potato, and there's literally trillions of them down there. Now, I mentioned the demand, mineral demand for technologies that will need metals in order for us to have electricity and have power in a renewable energy future. So a renewable energy future is a future where we generate electricity, in this case by windmill. And the windmill makes electricity, then it gets stored in batteries. And we've gotten spoiled in that we humans like to be able to have electricity whenever we want it. And fossil fuel is particularly good for that because you can just turn on the furnace and burn it when you need it. But we're going to have to get clever about this and find ways to generate it through wind, through water turbines, through sun and other ways, and then store it in batteries. And batteries can be recycled over and over again. I mean, the metal in the batteries can be recycled infinitely. The atoms do not get changed. Think of it like an elastic band. You pull an elastic band out and you set energy and you release it and you capture that energy. That's kind of how a battery works. And it requires certain metals. Nickel, cobalt, manganese are some of them. And these nodules are particularly rich in these particular metals. Now, I've taken cars here as an example to sort of walk you through how this might work. There are other needs for these metals. All steel needs a lot of manganese. Most of the developing world that doesn't have the kind of metal world that you have. You're all probably sitting in an office or in an auditorium right now. And if you look around you, you'll see metal everywhere in your life. And it's in the building, it's in your car. And we kind of take it for granted, but it's a mark of development to have a lot of metal in your society. And it requires these metals that you see listed down here at the bottom: copper, lithium, nickel, manganese, cobalt, etc. And cars are one thing that we do know we're headed towards, is electrifying our cars. There's predicted to be about 1 billion cars on the planet in 2050, and they should all be electrified by then and charged, importantly, with renewable energy, not with traditional fossil fuel energy. And this gives you an idea of the kilograms of selected minerals needed per vehicle. In a conventional car, you need this 20, 30 kilograms of metal for the chassis and the rest of the parts. But for an electric vehicle, you need a whole lot more, because the battery is most of the weight in an electric car, is the battery. And where's that metal going to come from? Traditionally, we have gotten the metal from the land. And my notes here. So there's good news and there's bad news for metals. Metals can be recycled. And that's wonderful. We will get to a point when we have enough metal in circulation that it's called closing the loop of that particular material. We won't have to get any more from good old Mother Earth, unlike oil, which is not recyclable. Oil, once you use it, it's gone. But metal in the form of a battery can be used over and over and over again. The bad news is that we don't have enough metal right now to meet the demands of this renewable energy future. We need to get it. And traditionally, we've gotten it, well, okay, so the 20th age of fossil fuels, age of metals, we've been over that. We're in the age of metals now. And this gives you an idea of where it comes from currently. The oil and natural gas comes from these countries, and these key battery metals are obtained in Australia, Philippines, Russia, Australia, Chile, Peru. Interestingly, the United States does not have natural reserves of these metals, and it's of some concern to any country that doesn't have the key material it needs to operate within its borders or safely within its borders of allies, because it doesn't ever want to be cut off from these. This is the geopolitical landscape that we're looking at. Now, the lithium-ion battery supply chain, the share of the global supply of selected stages in 2018, you can see that China is way out there. They have a lot of this stuff and are well positioned. It's just the geology of China is that they naturally ended up with terrestrial deposits of these metals. Here's give you an idea of critical metals for an electric car. You might need 85 kilograms or 56 kilograms of nickel, 7 of cobalt, 6 of manganese, and again, most of the weight, most of the material is in the battery of the electric car. The electric cars are very heavy. One thing that people don't realize, unless you try to pick one up, they are very heavy things, and they're mostly the battery. And battery technologies have gotten so good that it looks like the car will wear out around the battery. The battery will still be in okay shape, but the rest of the car will have to be redone. But in any case, we are not going to throw this metal away. We're going to have a robust global system of recycling so that we don't get caught in a trap of continually taking from the earth and not giving back, if you will. Now, what does it take on land to electrify a car? You can see here that it takes 156 cubic square meters of land to get the metal for one electric car. And this is the kind of activity that happens on land. Nickel is the biggest number, and it's the easy to get at nickel. The high ore grades have already been gotten because we've been mining for so long. So now we go after what's called nickel laterite deposits, and it's nickel, it's in the soil underneath tropical rainforests. And unfortunately, the deposits of these metals maps pretty closely with high biodiversity areas on land. So in order to meet these demands, we would need to be digging up tropical rainforests to get down to the nickel. And most of these are in places like Indonesia. Do we want to do that? There's also a lot of other things associated with mining. Carbon dioxide stored in the plants, in the soil, gets disrupted as you dig it up. And then there's extra CO2 emitted from other land use change as you mine this stuff from the land. Mining is the dirtiest thing we do on this planet as humans. It's produces the most waste, the most carbon dioxide. It kills people because of the hazardous way mines are put together. And it occurs in some of the most biodiverse places on Earth. It's just not a good way, not a good use of the planet to dig up these metals in these areas that produce so much destruction and so much waste. Sadly, there's child labor associated with a lot of the cobalt that comes out of the Congo. They use small children because they can climb down these holes and get the cobalt. It's so valuable that the kids are out here doing this instead of being in school. Also not a very good way to do it. There's a lot of waste from terrestrial mining. A lot of it is what's called overburden. It's what's on top of the metal that you've got to move around. And very often you'll be tearing apart a mountain for 1% or less of the mountain has the metal. The rest of it is waste. And the waste has to be put somewhere, and it's put in tailing dams. And sometimes those tailing dams give way, and you may read about it in the paper once in a while. You'll hear about a tailings dam, and there was one in Brazil a few years ago that killed several hundred people in a village that lived near it. It's a dangerous way for people to get this, and you end up with these waste piles. And they're even putting this waste in the ocean in some places. They dig it up on land, and then they just dump it in the ocean in deep pockets. So you're destroying the ocean and the land at the same time to acquire these metals. The way these metals are put together on land is fundamentally different than the way they're put together in these nodules. On land, you need to use different chemicals, and toxins emerge that you have to deal with through the process, arsenic being one of them. It's a very messy business. For anybody that's ever seen a mine, you'll know what I'm talking about. We don't have too many in the United States because we don't have the deposits, but we also don't have the stomach for it. Our communities don't like mines, and they'd rather the mine be on the other side of the world in a country that we don't really have a lot of empathy for. This is what's going on right now on land to get these metals. It destroys hydrological systems, it destroys agricultural systems, and as I said, it hurts peoples. This is that flood of mud that I mentioned when a tailings dam gave way and smothered some villages in Brazil. And a lot of this is the remaining nickel and other base metals are in these high biodiversity areas in Indonesia. So if we're going to fill these big gaps coming up to get us into this renewable energy future, we're going to have to go there. The footprint for just 4 metals for one electric vehicle is pretty darn big. It's you got 58 tons of toxicity, 58 tons of water, 64 tons of solid waste, and you've got 13 tons of CO2 emission. This is just one vehicle. This is what happens when you take it out of the land. Now imagine 4 metals for 1 billion electric vehicles. It would be 155 million metric tons of metal, which would cover the park in New York quite high. It's a lot of metal. And we're going to get to the ocean now as an option. It's something that we're looking at, and it's not the perfect solution, but we don't live in a world where we have a lot of perfect solutions. There's prices to pay. There's trade-offs that have to be made, and there's got to be a way to make this slide change, but I'm having a hard time finding that way. Oh, there it is. Going the wrong way. So on land, in order to meet the needs, now we're just talking about the electric vehicles here, not talking about all the other metal needs that the earth has or that civilization has. But just for land, for the vehicles, we're going to disrupt an area that would be the equivalent of what you see here, which is, it looks like most of upstate New York and other parts of the East Coast. In the process, we'll be destroying biomass, including very cute animals like this primate, orangutans and others. This will take out a significant bite out of the remaining carbon budget. Now, you may know that the UNFCCC, the UN body that's been looking after this climate crisis, has given us some guidelines about how much carbon we're allowed to emit between now and the near-term future. And if we can stay within that boundary, we have a chance of not having a runaway climate. And 13 gigatons is a lot. And that's what would happen if you took all this metal out of the land. Again, more visual comparisons of what we're talking about. There's a lot of material, a lot of change that happens, but you don't see it because it's happening in places that you don't live. It's happening in places where the people don't have as much to say about what happens in their environment that we do in parts of the world where there's more participation by the population. So we need virgin metals in order to populate the system and then recycle it in a reusable production infrastructure. And that's something about that our company is all about, is finding a way to get to a point where we're not taking more metal out of the earth. And we think reducing production and demand is part of it. Maybe we don't need 1 billion cars. Maybe we should cut it down to, 700 million. We should look at every way possible to cut down the demand for this, but there's always going to be a demand. We just don't have enough lying around in dumps. Some people think that we should go to the dumps and find metal. We should, but we should also look, there's not enough there, but we should also be doing look at other options as soon as possible. There couldn't be anything more important than this problem that we're having today is climate change. We have to decarbonize and detoxify virgin metals. This means that we really have to take a planetary perspective. We can't just look at a small area and say, oh, look at the damage that this caused in this small area. I don't like that. You've got to get your wide angle lens and look at the whole Earth as a whole and decide on a planetary basis what is the best option. It's possible that there's a better option for the supplying these metals, and that is the special case of these polymetallic nodules, also called ugly little rocks lying in the darkest depths of all creation. And they sit there on the seafloor, thousands of miles from anybody, and they're loose. You don't have to blast them out. You don't have to dig them out. You suck them up with like a vacuum cleaner. And they're very high grade source of these metals. They were first discovered in the 1880s. And since that time, scientists have studied them more and more, and we understand them. We've developed metallurgical processes where we can process them with zero or near zero waste and no toxic waste, importantly, which is very hard to do with terrestrial deposits. Here's some of the toxic elements often coming out of land. You need 4 times less ore to process and you have zero solid waste, as opposed to the overburden and the rock waste from land. It's a much more efficient way of getting metals. But we will be disturbing the seabed in an area offshore 4 kilometers down. And the way this is regulated through the UN, we're conducting a 3-year environmental impact assessment to remove every problem that we can and minimize every problem that we can't. And we can dramatically compress the footprint of getting these metals if we go to the ocean in the form of polymetallic nodules, we believe. We're still proving this with many days at sea. We're spending lots of money to get this right, to do the best science. We believe we may be the first entity to be putting forward an environmental impact assessment, and we want it to be a good one because we want all the other countries and companies that follow to have a standard to put their study up against, and we're going to set that standard. The one comparing the area used is you need a lot more area in the ocean than you do on land. So on land, you need 149 million square kilometers total land area. And in the ocean, you need 361 million square kilometers. But remember, the ocean is 70% of the planet. So, and it's coming from the abyssal plain, which is the largest habitat on the planet. So this, even though it's larger, relatively speaking, it's not as large and not as impactful as getting it from land. I keep losing the pointer here. There it is.
Hey, Dr. Stone.
Yeah.
So sorry to do this, but it is 1:17 now.
Oh dear.
We
Okay,
wanna-
I've gone on too far. Okay, I think I can wrap this up. I think I've made my point. I think I've made my point. Just remember, there's a column of water out in the ocean. It's different than land. We're studying every single aspect of this, and we believe that this has to be looked at, and I'm proud to be involved with this. I think it's the way forward. And in the end, again, we're looking at blockchain techniques for recycling so that we can make sure we get it all. And in the end of the day, you might find a label like this on your car to see what your car has done to the earth. Thank you very much for your time. I'm very sorry for going on so long. I get caught up in this. It's a very exciting thing for me, and I'm happy to take any questions.
No worries. Thank you so much. That was an awesome presentation. We probably can fit in like 2 questions because we did go over. And we got 2 here. So I will ask you from Tom. Tom wants to know, when Arctic cold water sinks to the bottom of the ocean at the pole, what causes it to turn into a current, and what force moves it south? And also, why does it follow a specific path if that's true?
Well, it depends. It depends on what it encounters when it hits the bottom. In the Arctic, there's no land, so it can go north or south, and it does. But when it sinks around the Antarctic continent, it's only got one way to go, and that's north, because there's a continent sitting on the South Pole. So that's what determines that. It's really a result of the geography of the seafloor.
Got it. Okay, last one from Miriam. During mining, some metal particles leak into river streams and oceans, polluting them. My question is, what happens when marine creatures ingest them accidentally? And can you please explain the term biomagnification?
Sure. Biomagnification is a term which every time you have a food chain, small animals are eaten by bigger animals. Those bigger animals are eaten by even bigger animals. So as they keep eating, whatever was in the animal gets ingested and taken into the bigger one, and it gets magnified because you've got several layers of this going on at the same time. And yes, not just metal pollution, but all kinds of pollution is biomagnified in that fashion.
Well, Dr. Stone, thank you again for your time.
Yeah.
I probably have like 10 questions I could ask you from your presentation, but unfortunately we're out of time. So again, thank you. And again, just wanted to remind everyone that tickets to Blue Hour Ocean of Inclusion, they are going fast. So please don't miss out on this incredible opportunity to attend this
gotta
event on
come.
October 9th. Yes, exactly. Got to be there.
I'll be there. You can ask me more questions there.
Beautiful. See, you can come see Dr. Stone, support Altasea, and be sure again to use the code AQUA, AQUA, for a 20% discount on your tickets at altasea-project-blue.org. Dr. Stone, thanks again for your time. I really appreciate it,
Thank
and
you,
our
John.
audience loved it.
Yep.
So
I love
have a great
Altasea.
weekend, everyone.
Yeah.
Have a great
Thank you
weekend.
very much. Yeah. Bye.